Bismillahirrahmanirrahim. Today is our lecture number 24. Dilemma 5. Dilemma 5 states that let the following diagram of R module and their R homomorphism. Basically, in lecture number 22, we have studied dilemma 3. After this, dilemma 20. And in lecture number 23, we have studied lemma 4. But in this lecture, we have studied lemma 5. Basically, a lemma 2 contains basically two squares. In lemma 3 and lemma 4 basically contain three squares. But here he add another squares like d from k and e to e dash and d dash to a dash. Be commutative with two exact rows, then alpha, beta, del, gamma are isomorphism implies that gamma is so. Basically, lemma 5 contain one parts. Lemma 5 states that basically when alpha, beta, and del and lambda are isomorphic, alpha, beta, del, lambda is isomorphic, so is gamma. What is gamma? Basically, gamma is also isomorphic. So by previous theorem, apply the lemma 4 to the right hand square of the given diagram. Given gamma is R epimorphism. Again apply the same lemma by the left hand square of the given diagram. R is R monomorphism, hence R is isomorphism. Because in the last lecture we have studied lemma 4. Lemma 4 states that when alpha, alpha, gamma, and del is a monomorphism, then beta is monomorphism, and similarly it is epimorphism, so beta is epimorphism. So by combining, by applying these both conditions, we have proved that alpha is R isomorphic. After this, we have studied corollary. Let the diagram in above lemma be commutative with two exact rows, then alpha is onto beta del are 1 1 implies that gamma is 1 1. Our second, gamma is 1 1, beta del are onto, then gamma is onto. So there is very well known corollary. You should try to resolve it. After this, we have studied definition. This definition states that two short exact sequence like O to A to B, B to C, and C to O, and O to A dash to B dash, B dash to C dash, and C dash to O of R module and their homomorphisms are said to be isomorphic if and only if there exists isomorphism F from A to A dash, G from B to B dash, and H from C to Z dash such that is commutative. These two short exact sequence is said to be isomorphic if for this there exists three functions which is defined F from A to A dash, G from B to B dash, and H from C to C dash is isomorphic, then the diagram is commute. After this, we have studied some remarks. These remarks basically state that the isomorphism relation of a short exact sequence of R module and their homomorphism is an equivalence relation. So this is a remark. After this, we have studied what? Basically, this is lemma, the short 5 lemma. One is the lemma 5 and this is the short 5 lemma. Let's see what short 5 lemma state that let the following diagram of R module and their R homomorphism this. Basically, this function is taken from the last definition like this. Yes. basically from here. This short 5 lemma basically contain this diagram. So this diagram is commutative with the two row of short exact sequence. Then if what this theorem states that alpha and gamma are monomorphism, then so is beta. After this, alpha gamma are epimorphism, then so is beta. Number third, alpha gamma is isomorphism, then so is beta. Basically, this theorem consists three parts. In first part, we show that alpha is basically what? Monomorphism. So basically, epimorphism, and number third, isomorphism. Basically, one onto and bijective. So let's start the proof of this theorem. Basically, we are already proved that in a lemma 4, we already proved that beta is 1, beta is onto, and beta is bijective. So basically, this is the special part of the special case of lemma 4 also and lemma 5. So basically, let's see the statement of lemma 5. This is lemma 5. So basically, this is the here we prove that these functions are isomorphic, so is gamma. So gamma is also isomorphic, and this is the generalization of lemma 4. So we have proved that what? Basically, this sequence is also isomorphic. Here, when we are study this sequence, so this is basically two squares. Like f is defined from a to b, alpha is defined from a to a dash, f dash is defined from a dash to b dash, and beta is defined from b to b dash. Similarly, g is defined from b to c, gamma is defined from c to c dash, and g dash is defined from b dash to g dash. So basically, this short 5 lemma is contain two squares, is commutative, and from here we get image of f is equal to kernel of g, image of f dash is equal to kernel of g dash. Similarly, beta composition f is equal to f dash composition alpha, gamma composition g is equal to g dash composition beta. So by using these things, we have proved that what? Alpha and gamma are monomorphism, so then b is also monomorphism. Alpha gamma are epimorphism, then beta is also epimorphism. Alpha and gamma are isomorphism, so then these are isomorphism. After this, module with chain condition. Basically, chain condition and ascending chain condition in the sense of theory of module we are already studied in Dr. Lekha's sub notes, but here also revised because if maybe you feel something misunderstanding, so here inshallah I will explain very deeply, and I hope you will understand easily. So let's start definition. In our module, let M be in R module and Sm denote the set of all submoduli of M. Then Sm is an ordered set ordered by the inclusion relation subset. Means that one subset is contained. When this is the ordered set, basically ordered set, and basically in many examples we have used this are equal, but here is a set, so we have used a subset. Sm is said to be satisfy the ascending chain condition if every increasing chain of submodules this M1 is contained in M2 is contained in M3 is contained in Sm is stationary. Stationary mean that at their time comes in this is increasing chain. Basically, a stage is come when they start a repetition, like mn is equal to mn plus 1 equal to mn plus 2 equal to mn plus t. So this kind of sequence is called ascending chain condition. And similarly, if we have changed this symbol like superset. M is the subset of superset of M to superset of M. So this is called decreasing chain condition. Okay. Sm is said to be satisfy the maximal condition if and only if every non-empty subset of Sm has maximal element. We have already studied what is maximal element, what is maximum, what is ascending chain condition, what is simply chain condition, what is Noetherian, what is Artinian. So we have already studied these things, and I hope you have no complication in this result. After this, we have studied very well-known result. Sm satisfy ascending chain condition if and only if it is maximal element. So this is very obvious because a set is contained, for example, M1 is contained, M2 is contained, M3 is contained, and in this stage we say that Mn is the maximal. So that means that no, there not exist no one Mn plus 1 such that Mn is contained in Mn plus 1. That means that there starts like stationary. Mn is equal to Mn plus 1, Mn plus 2. So this is very obvious when Sm satisfy ascending chain condition, so its maximal contain must maximal condition. So it is straightforward. After this, we have studied remark. If Sm is ordered by this set, you know, before I also say when we are convert this symbol by superset, then what? Then the descending chain condition and then the descending chain condition. So I said that this chain is converted to descending chain condition and the maximal condition are equivalent. So the maximal is converted to minimal. Okay. After this, we have studied some definition like in our module M is said to be Noetherian if it satisfies ascending chain condition. So before we are also studying in the chapter Lakers subnodes, we was already studied what is Artinian, what is Noetherian, and also teach some theorems related to Artinian and Noetherian. So this is basically just the special part of these theorems. Like we are taken the first part of the theorem, some theorems contain this second part. So basically we are already done it. So R is in R module M is said to be Noetherian if and only if it satisfies ascending chain condition. After this we study corollary. In our module M is Noetherian if and only satisfy maximal condition. So this is obvious. So inshallah, after this we will study in our next lecture. Inshallah we will meet in our next lecture. Allah Hafiz.